So welcome to session number 2 of the module 5, where we are discussing about design of power screws. So in the previous session we looked at the definition of power screws, how they are used, or the basic terms in power screws. So basically power screws are nothing but thread elements, and which are used to transmit the power or to hold the load. So basically the power screws, they have threads. So in the previous chapters or in the previous sessions you have learnt about the threads, different forms of threads, and also in previous semester courses, particularly in machine drawing, you might have learnt about the forms or the forms of threads or different threaded forms. So hope all of you are familiar with these forms here. So we'll just have a review of these thread forms which are used in power screws. So in threaded fasteners, there are some forms compared to power screws. Those threaded or thread forms are not used, may not be suitable. So the thread forms which you learnt in your other courses or previous sessions, in that some are used in threaded fasteners, whereas some are, they're not suitable for power screws, and we look at some other forms of thread. And all of you know about these threads, but some forms are used in other words I can say that different forms of threads are used, and some are used in threaded fasteners and some are suitable for the power screws. So we look at some thread forms which are basically used in power screws rather than threaded fasteners. So the purpose of the threads in fasteners is to provide high friction, or what is called to minimize the chances of loosening. So as I told you in the previous session, the application or the operation of these power screws compared to the fasteners or threaded fasteners, they have high friction applications. So there you have to minimize the chances of loosening. So we are actually clamping together two different components using fasteners or nuts and bolts and screws, whereas in power screws the requirement is low friction, because we have to hold the load or to transmit the forces or transmit the powers. So low friction concept is used in power screws between the nuts and bolts. So that's the main difference between threaded fasteners and the power screws. So for that, based on the applications, we use different threaded forms or forms of threads in power screws. So basically we use these three types of forms of, or what is called as threaded forms or forms of threads in power screws. So here we have the one simple and basic thread form is the square thread. So as you can see here in the diagram, in the drawing here, we have the pitch. So these are the threads. So one side it is shown here, it is a cut section. So one side of the screw rod is shown here, which have threads here. So this is the profile of the thread is a square, you can see here. So it's called a square thread. And pitch is nothing but you take a point on one thread and the corresponding point on the next thread. The distance is taken as pitch. And in case of square thread, we have the depth here or height of the thread here from the base, from the root here. So usually it will be half of the pitch. So if this is pitch, the thickness height of this thread from the root will be h, half of that. So that is one form of square thread. So similarly we have acme thread or trapezoidal threads. So the acme thread, as you know, it is a slight variation of the square thread, where the angle between these two edges, so you can see here in case of square thread, this edge is perpendicular to the axis or bottom. So in case of acme thread, this edge is slightly inclined, and the angle between these two inclined surfaces or the threads is around 29 to 30. That's the modification what you can see in acme thread. And we have one more thread form, that is buttress thread, and you can see the profile of the thread is in this manner. So you can see it's again the modification of this thread. So you can see the thread edge or the face is angled here or inclined here in case of acme, and in case of square thread it is perpendicular. So here you can see both are combined here. So in case of buttress thread, one edge or one face of the thread is perpendicular to the bottom, whereas other face, the opposite face of the thread, is inclined at 45 degree to this vertical here. So the concept of inclination and perpendicularity is both are included or combined in this form here, and that is called as buttress thread. And other dimensions, relative dimensions, are you might have learnt in your machine design how to give these other parameters or other geometric dimensions of these threads. So we'll just review some of the important concepts of the different threaded forms. So in that we'll see the square thread. So as you can see, the face or flanks of the thread are normal to the axis. You can see here, these are the flank or face of the thread. They are perpendicular to the axis. So this is the axis of the thread. And because of this profile, the manufacturing feasibility is difficult here. So because we have the sharp edges 45 degree, so machining or manufacturing of this thread becomes a bit difficult, because we will be using different tools to cut this profile. And again, just like any other power screws, this threads is used to transmit power in machine tools, and it can transmit power in any direction. That means you can transmit power either left side or the right side of this threads here, and the efficiency is maximum compared to other threads. So usually in screw jacks we see this kind of threads here. Coming to acme threads, as I told you, the flanks or faces are not perpendicular to the axis, they are slightly inclined, and the included angle is 29 degree between the two flanks or faces of the thread. It comes to 29 degrees. So it is a modified form. So you can see it's a slightly modified form or modified version of the square thread, and compared to square thread it is stronger in case of the strength of that or efficiency, and it can be cut, so that is manufacturing feasibility is easy compared to the square threads. That's why that perpendicularity is eliminated and the faces are inclined to ease the manufacturing of these particular threads. So can be cut with taps and dies, and it is easy to manufacture because of this profile here. So you can see here it offers increased area and shear at the root. So here since the faces are inclined, so the shear force or the shear area will be more compared to the square threads. So all this shearing and the stresses will look at in the next sessions while we are analyzing the power screws. And again, these are used in lead screws and bench vices. So usually in lathe lead screw we have the acme thread, and even in your bench vices we use the acme threads. And we have one more form of acme thread, so slightly modified, or a small change is made in the acme thread with respect to the angle. So in this we call this as trapezoidal threads. So only difference is it is 30 degree. So the thread angle is 30 degree, and it is standardized by ISO here. So it is trapezoidal is similar to acme thread, except that thread angle is 30 degree. And we have buttress thread. So as I told you, both it is the combination of square thread and the acme thread. So one flank is perpendicular, other flank is inclined at 45 degree, and we have other dimensional parameters of this buttress thread here. So it can transmit large forces only in one direction. So because of this profile, so the forces can be transmitted in one direction, and it is stronger compared to other threads. And efficiency is the combination of square thread and the acme thread, and also ease of cutting is easy. So it combines the efficiency of the square thread, so it is efficiency is more, and also the ease of cutting is easy compared to square thread and the acme thread. That's why a small modification is made to combine the high efficiency and the cutting or manufacturing of these threads here. So both are combined here. Both the advantages of square thread with respect to efficiency and advantage of acme thread with respect to cutting is combined here, and we get the buttress threads. And again in buttress thread is light, again this edge, it is slightly inclined. It can be inclined based on different applications by a small amount of degree here. So it is also a buttress thread. Okay. So coming to designation, or how do we mark the power screws or threads in different drawings, machine drawings. So you might have seen about this term here. So we have single start threads and multiple start threads. So in case of single start threads, we simply give this number, and this number is nothing but the pitch in millimeter. And you can see SQ stands for square, and this number 28 stands for the nominal diameter of the screw rod. So if into this star mark is there, fine. So after the star mark, whatever number is there, it is the pitch. So and you have the TR represents the trapezoidal form of the thread, and it is a single start with pitch 6, and the nominal diameter of the screw rod, is 32 mm. Whereas in double start or multiple start threads, so you can see here in the bracket we are giving the pitch P, small p, that is pitch 6, and this number to the left of this pitch is the lead. So you can see a 6 into 2 is 12. So you can say that it is a double start thread, because 6 into 2 is 12. So 6 is the pitch into 2 is the number of starts. If it is double start, it is 2, so 6 into 2 is 12. So this becomes the lead. So this is how the multiple start threads are designated. The remaining remains same here, all the things. So you can say that number of starts into pitch gives the lead. And we have right hand thread and left hand threads which are given as RH and LH. So you can represent this TR32 star 12 P6 RH. It's right hand thread. This is the pitch. This is the lead. So it is, since it is 6 into 2 is 12. So you can say that it is a double start thread, and 32 is the diameter of the screw rod, and the form of the thread is trapezoidal. So again in single start thread, as I told you just now, we have only the pitch and the form here and the screw diameter. Whereas in multi-start we have the pitch in bracket, and we have the lead is also mentioned here, apart from the form of the thread and the diameter of the screw rod. And also you can use the data handbooks. In data handbooks, the standard forms or standard dimensions of the different threads are given in the data handbooks. So now the important part is you have to analyze or you have to design the square threads, or you can say you have to design the power screws now. So in the power screws, we'll assume that, or we'll take the we'll design for standard square threads, and we'll see how to design or how to analyze the loads or forces which are applied on the screw rods for different applications. So particularly analysis means we'll be understanding or we'll be finding out the torque and efficiency of power screws. So analysis is done by considering it as equivalent to raising or lowering of the load on an inclined plane. So here you can see this is a thread is there, a power screw is there, this is the diameter of the screw rod, and we have the threads here, and the angle of this thread is alpha, or what is called as helix angle. The thread angle is alpha. So here to analyze what we are doing is we will develop this what is called as a cylindrical part of this thread. So when you develop that, what happens, it will become a triangle like this. So this is the pitch and this is the lead, depending on the number of studs that is there. So this vertical height of the triangle will become the pitch or lead, and if you develop the circle or the cylinder, so that radius, the development will be equal to the perimeter of that circle. So that is pi d or 2 pi r. So after developing this thread or the cylindrical part of this screw rod, we will get this horizontal dimension as 2 pi r or pi d, and the height will be equal to the lead or pitch. So this is the inclined surface of the thread here. So since the threads are inclined to the axis or the horizontal, so this thread form or the face will become the inclined surface of this triangle. We can see this is again the threads here. The same thread is given here. It is cylindrical thread, and it is developed. So its development of this is you open the cylinder and we get the perimeter in the x-axis, and in the y-axis we get this the pitch or lead, and this is the inclined surface on which the load is applied, or we want to raise this much amount of load, raise or lower the load using the power screws. So this is just an analogy. So we are analyzing the square thread or the power screw with respect to the development. We develop this particular cross section of the thread and we get this triangle here. So this is the inclined surface. So on this surface, whatever load is we want to lift or we want to rise or we want to lower, that will be placed here. So the weight will be placed on this inclined plane. This is the perimeter of this circle. So this is the top view of this screw rod, and dm is the nominal diameter of this screw rod here, or mean diameter of the screw rod, and this is the force required. P is the force required to move or to rotate the screw rod. So force is applied and we are multiplying it by radius, that gives the torque. So what is the torque we have to apply to maintain this load or to raise or lower this load, that is analyzed here. So it is basically the moment of nut and screw, that is nothing but we are using it to move the load axially. It is analogous, it is an analogy to move a load or weight on an inclined plane. So this whatever load is lifted or raised by rotating the screw is equivalent to this triangular form, and it is equivalent to the load which is moving up and down of this inclined plane. So this is how we are analyzing. So the analogy is that you convert this, you develop this screw rod and we get this triangle, and on this inclined plane the load can be lowered or it can be raised. So the torque, the whatever load or force you are applying to maintain or to lift or to lower this load, that gives rise to torque. That is the torque we can analyze, to the torque required to rise or lower the rod. So rise or lower the load means whenever you rotate the screw rod, it will lift the load, or it may drop the load. So that is the torque required. You have to calculate P, and weight is the load applied on the screw rod, which has to be lifted or which has to be lowered in application. So the same development is given. So this is the screw rod top view, front view and top view, and when you develop that, when you open that surface, we get the triangle with pi dm in the x-axis, and the pitch will be the y-axis, and this is the inclined plane. So on this inclined plane, the load will be there, and this load has to be lifted or it can be lowered based on how much force you are applying or the torque you are developing there. So here to analyze, we'll start with the analysis now. So in the analysis, this pitch, anyway the pitch will be there for the thread, and alpha, so this becomes the alpha, the helix angle. So this is the thread helix after the development. So the inclined plane will become the surface of the thread, and the angle, thread angle or helix angle, will be alpha. dm is the mean diameter of the thread, so we take the mean diameter of the thread screw rod, and F is the axial load, so F or P. So in some cases we take in some cases we take it as W or F. So different textbooks or different authors, they use different annotations. So here, since we are referring many books, so F is nothing but the load or weight. In this case it is W here in the diagram, whereas this P is the force, external force you are applying to maintain this load. So F or W is same, annotations are same, the load or the weight F. And when you develop the screw single thread, we get this triangle inclined plane, and the length, the height of this plane or this triangle will be equal to the lead. So lead is again, it depends on whether it is a multi-start or single start. So if it is multi-start, you multiply it by n, number of starts into pitch, or if it is single start, this L will be equal to pitch. So you can see the power screw here. This is the nut, and this is the diameter, mean diameter of the screw here, or the thread here, screw rod. So this is the screw rod base minimum diameter. This is the external diameter of the screw rod, outer diameter of the screw rod. That average is taken as the mean diameter of the screw rod. So all this you have learnt in the previous sessions in machine drawing. So just use that dimensions here. Just recall those dimensions. So this is the pitch. So pitch is nothing but the distance between the threads, and this is the angle, alpha, helix angle, thread angle is, this is the helix angle is given here. It is nothing but we call this as simply helix angle. So this is the helix here. So at what angle it is with respect to x-axis is taken as alpha. So this alpha is here. So we make the analogy. So this is the load which is applied on the screw rod, which has to be lifted or which has to be lowered. So when you rotate this screw rod, we can lift this load or we can lower this load. This is a collar which is fixed on which the load is applied, and this collar is fixed to the screw rod here. It is just a platform for the application of load. So you can see the power screw system is nothing but we have a screw rod and the nut and the frame or the collar on which load is applied. So these are the dimensions you have to remember while analyzing the screw rods. So this is the load F for W. You can see F for W is applied here. Small p is pitch. This is the helix angle alpha, and the dm is the mean diameter. And when you develop this portion, the single thread, we get this wedge shaped element here after developing. So the load will be applied on this inclined plane, and the perimeter of the circle will be equal to pi dm, and this height of the triangle will be equal to the pitch or the lead. So the same is analyzed here. So we take any cross section. So this is screw and this is a nut. So how the load is applied, the force or W is applied, and this is the helix angle, inclined surface angle or the helix angle alpha. So the screw and the nut load is applied here. So this becomes a inclined plane, and this is a triangle with pi dm as the length and height as the lead here. This is the development of this thread, single thread. So single thread is developed and we get this triangle here. So as I told you, to analyze the mechanics of this power screw, or how the forces are applied and how the forces are reacting, and here basically what you are doing is, as I told you, power screws are used to transmit the power or load. So in power screws, while rotating the power screw or the screw rod, you can raise the load or you can lower the load. So basically we will try to understand the mechanics involved in raising the load and lowering the load here. So first case we'll see about raising the load. So this is about raising the load, and in case of raising the load, this is the development of that single thread. Just now we saw this is alpha, this is the inclined plane, and on this inclined plane the load is applied here. So you are raising the load now, so whatever load is there, it has to be raised. So the load is acting like this on the inclined plane, and this is the length, pi dm is the length of this triangle, and the height of this triangle is the lead or pitch. So once you are applying the force, the load is, sorry, this is the weight or the load which has to be lifted, which has to be raised. So we have to apply external force in this direction. So the external force or torque is, we are taking it as P. So this F is the load or weight which has to be raised on the inclined plane, and to raise this load I have to apply an external force or load or the torque P in this direction. So once the load is applied, the weight is applied on the inclined plane, we have the reaction normal N to maintain equilibrium of the load. A reaction will be there N. And also we have the, when the load is moving up or down, there will be a frictional force acting here. So mu N is the frictional force. So mu is the coefficient of friction here. Mu is the coefficient of friction. So whenever the load is, whenever you want to lift the load, so the load is moving upwards, the reaction force will be acting in this direction. So in simple mechanics, coming to the mechanics acting around this point, so we add all the forces in x-axis and y-axis for this equilibrium of the system, and we get these equations. So we have the force or the load acting downwards, we have the external force P acting in this direction, we have the normal acting in this direction perpendicular to the inclined plane, and we have this frictional force acting in this direction downwards. So the load is moving upwards, the frictional force is moving, it is acting downwards. So we have the forces acting at this point, and for equilibrium in mechanics we add all the forces in x direction and y direction, and the summation will be 0. So with that simple mechanics principles, concepts, so add all the forces in x direction. So this is the x direction, the external force is applied P in x direction, P, it is there here, and this mu N, the frictional force, you resolve this force in x direction, so it becomes mu N cos alpha. So this force, frictional force, is resolved in this x direction, and it is acting in the opposite direction, left side. So it is negative here. So mu1 into cos alpha. So it is acting on the plane. So resolve this in x direction. So it becomes cos alpha. And minus one more force is there. It is this force is acting perpendicular to this inclined plane. So resolve this force in again x direction. So it will be acting in this direction, negative direction of x. So it is negative here, and it is n. This is n sin alpha. So it is acting in this direction of this one. So resolve this force in this direction. So it becomes n sin alpha. So summation of that will be equal to 0. Similarly, summation of all the forces in y direction. So in y direction we have the load F to be lifted. So this F is there, F here, and this frictional force, resolve that in y direction. So it will be acting in the downward direction. It is positive, mu1 sin alpha, and again this n, you resolve this in y direction, it will be n sin n cos alpha. So using this simple mechanics or resolution of forces on the inclined plane in x-axis and y-axis, you will get these two equations, and for equilibrium the summation of forces will be 0. So you get two equations here when you apply the resolution of forces on this inclined plane. So we get these two equations, and if we take the ratio of that and modify the equation, we get this term here. So we are getting the equation with respect to P here. So this P is the external force what you have to apply, or external torque what you have to apply. F is the load which has to be lifted by the screw jack or power screw, and mu is the coefficient of friction, and alpha is the helix angle of the thread. So using these terms we get one equation here. So once that external force required P is known, we can calculate the torque. So torque is nothing but TR here, or simply T. So that is the force multiplied by the distance. So here distance is the radius. So whatever force you are applying, so whatever force you are applying here, sorry, so this force, so whatever force you are applying, external force to maintain this load, so this force will be nothing but the torque. So torque is nothing but force into the radius, or the mean diameter of the mean diameter. So that is torque here. The torque is the external force into radius or diameter of by 2. So that P, just now we calculated what is P. So that P we got just now with respect to the load here. We substitute this P in this, and we get this equation. So now the torque is expressed in terms of the load which has to be raised. And here one more thing, in the triangle, tan alpha is nothing but opposite by hypotenuse, or we're taking tan alpha is nothing but opposite by adjacent here. So tan alpha is L by pi dm. So tan alpha in this triangle is opposite by adjacent here. So if you take that and substitute L by pi dm as tan alpha, so if you substitute this alpha, or if we divide this by cos alpha, it will get the term tan alpha, and substitute L by dm, we will get the equation, or the torque equation, in terms of the nominal diameter of the thread or the screw rod. It's only substitution, only this equation you just remember, just substitute the values and rearrange the terms, that's all. Similarly, we have what is called as we have one more derivation or analysis where we'll be lowering the load. So in case of lowering the load, you can see here the applied or the weight which has to be lowered. You have to apply the force, external force in this direction. So you are trying to lower this load along this inclined plane. So you are applying the external force in this direction now. So in the previous case, the load was applied against the inclined plane to raise the load. The external force or torque was applied in this direction to raise the load here. Whereas in case of lowering the load, the external force or torque would apply in this direction. This is the external load, this is the inclined surface, and the load has to be lowered. It has to be lowered along this inclined plane. So we have to apply external force or the torque in this direction. So again, taking all the mechanics concepts, resolution of forces along x-axis and y-axis, we get these two equations, and doing the same simplification, we get the external load applied which is required here in terms of the work to be lowered or the load to be lowered. So here again mu is the coefficient of friction and alpha is the helix angle. So same thing again, torque is nothing but the force into dm by 2. Substitute that and you can express the torque in terms of helix angle, or you can express torque in terms of L by pi dm, because tan alpha is L by pi dm. So substitute that, we'll get this equation. So these two equations you have to remember to calculate the torque required, or the rotational force required to raise the load or to lower the load when the screw rods are applied for various applications. So here you can see we are just comparing both the equations what we derived just now in horizontal and vertical direction. So we are just comparing that, raising the load and lowering the load. It's just like differentiating or deriving. Equations are derived, both the equations are derived here. So this is the left side equations are with respect to raising the load, right side equations are with respect to lowering the load. So the equation just now we saw this, all these terms are there. And one more thing you have to remember here is mu, that the friction, coefficient of friction is nothing but tan phi. So phi is the pressure angle which is a term in the threads. So you can substitute that and you will get this equation. So the force required to raise the load will be equal to W. So W is the weight or the load which has to be raised, or F in the other case it is F. So the F for W tan phi plus alpha. So again you can see here mu is related to pressure angle. You can see this is the power, this is the load or the force required to raise the load, whereas this is the force required to lower the load in case of the screw rod or the power screws. So you can see here to raise the load, this term, that is helix angle, will be added here. To lower the load, it is negative here. So this is the only difference between raising the load and lowering the load. So W is nothing but F here. So in previously we had taken it as F here, now it is W, both are same, weight or F. So torque is nothing but, again you multiply this P into D by 2, we will get the same equations here. So both the equations are just differentiated in this table here. Left hand side we have raising the load, right hand side we have the lowering the load. So previously we were discussing about square threads. So this is all the derivations are for square thread, and if you take the trapezoidal thread or the acme thread, we have to make a small variation in the equation where the weight whatever the load is applied, it will be resolved along this inclined plane. So in square thread it was perpendicular, but in Acme thread the surface, the load on which the surface on which the load is acting, it is inclined. So we'll be resolving the force W or the load W with respect to this theta here. Theta is nothing but the thread angle. So if you look, if you make some changes here, just you have to make this W, the load applied perpendicular to this inclined plane will be W by cos theta. So this is W, and we have to resolve this force perpendicular to this inclined plane. So this load will become W by cos theta or W secant theta. So a slight modification is made with respect to trapezoidal screws here, whereas this equation is for these are all for square threads to rise or lower the load, whereas this is for the trapezoidal threads. A slight variation is made in the load in the applied load to raise the load, or to require, or to reduce the, or to lower the load W. That's it for the session. In the next session we'll look at some more concepts, and we'll try to solve some problems for designing the power screws. Thank you.